So yesterday we started talking about work energy theorem. Okay, work energy theorem says that work is. All right, so work, we said, is, according to work energy theorem, a change in mechanical energy. All right, and we can calculate work by multiplying force times distance. Right? Then we looked at this example of the two people using the inclined plane, and we said they both do the same amount of work in moving this mass to the top of the ramp. One person lifts it there, the other person pushes it up the ramp. Now, because the amount of energy the block would have at the top of the ramp is the same, regardless of how you get it there, they both change the energy of the block by the same amount. That's why they do the same amount of work. Okay? Now, it looks like the person lifting it should be doing more work because they have to exert more force. But they exert more force over a smaller distance. Okay? And so in the end, they both end up doing the same amount of work. Okay? So work energy theorem says work is a change in mechanical energy. That means you could be changing the potential energy of something, you could be changing the kinetic energy of something, or you could be changing both. Okay? First day of the unit, when we talked about mechanical energy, we said that mechanical energy is the sum of both your potential energy and your kinetic energy. Okay? It is possible to have both. It is possible for both to change at the same time. Okay, looking at this other example here with the pulley and the ball in the box here. Okay, so we've got a 5 kilogram ball hanging over a pulley attached to a 3 kilogram box. Okay, if I let go of this 5 kilogram ball, the ball will what? It'll fall. Okay, as it falls, it'll pull on the 3 kilogram mass. Is it transferring energy from itself to the box? Yes, it's doing work on the box. It's exerting a force on the box, okay, over a distance. Now, is its energy also changing? Yeah, okay. When it falls down to here, okay, it's turning some of its potential energy into kinetic, but not all of it, because some of its potential energy is being used to move the block. Okay, does the energy of the entire system change though? Okay, the total amount of energy in that whole system is unchanged. So remember, that's part of the law of conservation of energy. It says the energy of a system cannot be changed unless work is done to it. Okay? No more energy is being put into this system than there was at the start. Okay? All the energy in this system at the start is potential energy in the ball. Okay? This box really doesn't have any potential energy because it can't fall. Okay? So it gains kinetic energy because some of the potential energy of the ball is transferred to it, but the total energy of the system remains the same. Everybody all right with that? All right, so gravitational potential energy, we said yesterday, is affected by three things. Okay? It is affected by the mass of the object, the acceleration due to gravity, and the height from which the object falls. Okay? Those are linear or direct relationships. Okay? An object with twice as much mass as another will have twice as much potential energy, gravitational potential energy. Okay, that was, remember we said there's a piano falling off a building and a tennis ball falling off a building. Okay, you'd want one obviously be standing under the tennis ball, or neither, but definitely not the piano. Okay, it has more mass. And then our acceleration due to gravity. Okay, obviously on Earth that's kind of a fixed number. Okay, and then height. Right, if I take an elevator to the first floor of a building, I have a certain amount of gravitational potential energy. If I go to the second floor of that building, I will have more. In fact, I'll have twice as much. All right, now, units for everything. Obviously, potential energy is a form of energy, so it's always measured in joules. Okay, mass, or M, is the mass, and it's always in kilograms. In physics, we go big. In chemistry, they deal with atoms, so they go small. Okay, so in chemistry, all the masses were in grams. In physics, they're all going to be in kilograms. Okay, gravitational acceleration, okay, is 9.81 meters per second squared, and h is going to be the object's height above the ground. That needs to be in meters. The reason it needs to be in meters and the mass needs to be in kilograms and all of that is because a joule is a kilogram meters squared per second squared. Those are the fundamental units for a joule. Aren't you glad we just say joules? Okay? And it's a kilogram meter squared per second squared. Everybody all right with that? Okay. So, simple example of a gravitational potential energy kind of problem. Okay, I have a 3 kilogram box. It's lifted by an upward force 1.5 meters above the surface of the Earth to the top of a table. What is the potential energy of the box in its new position? All right, so they gave me mass, they gave me height, and they told me gravitational acceleration is 9.81. They're not always going to say Earth. If they don't say Earth, assume Earth. Okay? Unless they outright say some other place, or they say the acceleration due to gravity is some other number, assume always 9.81. All right, so all I have to do then is plug in my numbers, m times g times h. So 3 kilograms times 9.81 times 1.5 meters gives me 44.1 joules of gravitational potential energy. Right, so now that box has the ability to do work. If it falls off the table, okay, it can put a dent in the floor. So, right, questions on how that one works? Very straightforward. Okay, is this going to be a pretty easy formula to manipulate? Right? If I want to move anything, sorry, that's supposed to be a P, okay, all I have to do is divide it over, right? So that'll be easy to manipulate. Okay, so I want you guys to try this one. 55 kilogram diver standing on a diving platform, and they have a gravitational potential energy of 5,400 joules. Okay, that's 5.4 times 10 to the 3, not times 103. That's supposed to be 10 to the 3. Okay, so that's 5,400 joules. Okay, we want to find the vertical height of the platform. All right, give you a minute on that one. Okay, so for this one here, okay, obviously we're going to be using EP equals m times g times h, but we're trying to solve for h. All right, so EP equals m times g times h. I want to leave h over here, so what do I do with m and g? Divide both sides by it. All right, so that's going to give me my formula. So I'll have 5,400 joules divided by, and you're going to have to outsmart your calculator here, okay, 55 times 9.81. All right, when we do that, we should get 10.0 meters, okay, as the height of the diving platform. All right, so that's the tallest platform. Really, really tall Olympic diving platform. All right, questions on that one? Pretty straightforward. They don't get too. All right, now, kinetic energy. Okay. Kinetic energy is the type of energy something has if it is moving. It's the type of energy that actually does work. Okay, potential energy can't do work. It's just the potential to do work. It has to be turned into kinetic if it's going to do anything useful. All right, so it's the result of kinetic energy that we see doing things, okay, in life. Right? So when the potential energy of an object is released, that object often begins to move. Moving objects do work. Falling hammer can drive a nail into wood. Okay, moving molecules in hot steam can turn turbines. Okay, moving molecules in a sound wave can make an eardrum vibrate. Or parts of the human body, if moving fast enough, can break stuff. Okay, and it's actually pretty cool to see people like break stuff, okay, with their hands. Now, you actually don't often break stuff with your hands. Why not? You'll break your hand, yeah. Unless you're really well practiced and have been doing it for a very long time, you will likely break the bones in your hand because the bones in your hand don't have very much what? They're not big. They don't have very much mass. Okay? So as a result, if you hit something that's more massive than they're likely to break. Okay? Now, someone who trains often and working on getting better at breaking things, practices breaking things. And every time they do that, they get microfractures in their bones. The microfractures heal, and the bone gets stronger and stronger and more dense. Meaning, they can break stuff that you can't. Okay? So if you watch somebody who's been doing this their whole life wind up and break like 4 pieces of wood, okay, and then you go, well, that looks easy, you're going to break your hand, right? Because your bone density is nowhere near what theirs is, and you don't know what you're doing most likely. Okay? The key to actually being successful in not breaking your hand, or whatever part of your body you're using, is that you have to have the confidence that you are going to break whatever it is you're trying to break. If you hesitate, then you will have trouble. Because remember, work is force times distance. Okay? When you strike whatever it is you hit, you don't want to be in contact with it for very long. The longer you're in contact with it, the more likely that it'll have some elastic reaction that will come back and break your hand. So you can get through it really, really quickly, okay? Then you don't get that reaction and you're less likely to break your bones, okay? So what we're going to be looking at here is a couple of examples of people who are like really good at this, okay? I'm going to show you a video of the world record holder for broken sidewalk blocks. Okay, so you guys know what I mean by a sidewalk block? So it's a piece of concrete. Okay, they're about 1.5 inches to 2 inches thick. It breaks like over 24 at once. One strike. Okay, so they're stacked, similar to how these pieces of wood are stacked. Now, obviously they're not stacked right on top of each other. What is there between each block? There's a small space. Otherwise, nobody breaks that many pieces of concrete because it's actually then just one really thick piece of concrete. Okay, so there has to be a small space in between to allow for the change of shape of the sidewalk blocks to happen. Okay, if they're all on top of each other, then it's just one big piece. Right. So I'll show you that first. Okay, this guy is actually he's a veteran. He was blinded by an anti-infantry device, so he can't see. So he's actually led over to the big stack of sidewalk blocks, okay, and then proceeds to go superhuman and break. So, for kinetic energy, okay, kinetic energy is dependent on a couple of other things. Okay, so for potential, it was mass and gravity and height, but for kinetic energy, it's mass and speed, but speed is squared in this formula. So, as I go faster, the kinetic energy increases, but not linearly, it increases exponentially. Right? So, if I double my speed, I will have 4 times as much energy. If I triple my speed, I'll have 9 times as much energy. Okay? It's an exponential relationship. So there's an exponential relationship between speed and kinetic energy. Here's what that also means, and this is something you need to take to heart, because I do this every single semester. You guys are all kind of getting ready to get your driver's licenses. Maybe some of you have them already. Okay? There is an exponential relationship between kinetic energy and speed. That means that the amount of work required to stop you increases exponentially with your speed. Okay? So if I'm traveling at, like, let's say through a school zone at 30 kilometers per hour like I'm supposed to, I have a certain amount of kinetic energy. Okay? If I want to get rid of that kinetic energy, that is stop, okay, my brakes have to exert a force over a distance in order to change my kinetic energy from its initial value to a value of 0. Okay, so we're looking at the change here in kinetic energy. Right now, normally we would have 1/2 mv. So sorry, we'll write it the way it's supposed to be here. So the change in kinetic energy would be 1/2 mvf. So this would be my final kinetic energy minus my initial kinetic energy. But I want to stop, so this is actually, no, if I want to stop, what will my velocity be? What's anything times 0? Okay, so really, the amount of work that needs to be done to stop me is equal to the kinetic energy I have when I hit the brakes. Okay, because I have to get rid of all of it. Right? Now, what do my brakes do in stopping me? What do they? Yeah, they use friction. So they turn my kinetic energy into sound, heat, mostly heat. Okay, yeah, they just turn it into other forms of energy that don't involve me moving forward anymore. Right? So the distance then required for me to stop is exponentially related to my speed. So if I'm going 30 kilometers an hour, it's going to take me a certain distance to stop. If I go 60, I'm going to go 4 times as far before I stop. Hopefully nobody's stupid enough to go that fast through a playground zone. Okay? But here's what we all do. Okay? We all tell ourselves this, and we make it okay in our mind. It's just 10 kilometers an hour. It's not that big a deal. It's just 10 kilometers an hour. I'm only going 40. I'm only going 40 in the 30 zone. It's not that big a deal. But remember, any change in speed results in an exponential increase in your stopping distance. All right, so I'm going to illustrate this, what this looks like too. Let's say that my car, whatever vehicle I'm driving, can exert, let's say, 9,000 newtons worth of stopping force. Okay, that's how much force my brakes can exert if I pound on them and they're working perfectly. Okay, there's no ice, dry paper, and all that kind of stuff. Okay, and we'll say that the mass of my car is 2,000 kilograms. Okay, if I'm going the speed limit through a playground zone, then I'll be traveling 8.3 repeating meters per second. Okay, that's what 30 kilometers an hour is in meters per second. Okay. All right, so I've got force times distance equals 1/2 mvi squared. So if I want to solve for d, what do I do? Divide force over to the other side. Okay, so I'm going to divide both sides by f. So this will calculate my stopping distance if I'm traveling the speed limit through a playground zone. All right, so d will equal 1/2 times 2,000 kilograms times 8.3 repeating squared, divided by my stopping force, 9,000 newtons. Okay, so 0.5 times 2,000 times 8.3 squared. Okay, divide that by 9,000. And my stopping distance is 7.7 meters. And that's at the speed limit. Okay, 7.7 meters would be the distance from that wall to probably about here. It's a long way if a kid runs out in front of you, but that's the speed limit. Okay. Now, if I go at 40 kilometers per hour, it's 11.1 meters per second. Okay, so if I change this equation that we just did to now be going 40 instead of 30, look what happens to my stopping distance. So 0.5 times 2,000 times that 11.1 squared divided by 9,000. Okay, it was 7.7 meters to stop at the speed limit. Now it's almost double. I only went 10 kilometers an hour faster, but my stopping distance nearly doubles as a result. Okay, there's an exponential relationship between speed and stopping distance. Okay, that's something you need to remember. For some reason, that is not taught in driver's ed. Why? Okay, it should be taught. It's something everybody needs to understand. Okay, that 10 kilometers an hour that we all tell ourselves is okay, really isn't. Okay, that's a distance there of 7.7 to 13.7, so 6 meters difference. Okay, well, now instead of being right here, now I'm all the way into the hallway a ways before I get stopped. Okay, that's a long way if a kid runs out in front of your car. Right? But here's the other thing we tell ourselves. That 10 kilometers an hour is really, really important. Okay, so let's look at how important it is. A school zone, playground zone, they're not very long. Okay, they might be, let's say, at the most 300 meters in length. Okay, So if I'm solving for time, I'm going to take my 300 meters and divide it by how long or how fast I go and go on the speed limit. Okay, it's going to take me 36 seconds to get through the playground zone at the speed limit. Take me 27 seconds going 10 kilometers an hour faster. At the end of that playground zone is a stoplight, which is going to be red no matter which way, no matter how fast you go through the school zone anyway. Okay? But when we do this, we're saying that these 9 seconds are more important than that little kid who runs out into the street, because little kids don't look, they just go. So, your 9 seconds is the difference between me going home and having dinner with my kids or going home and planning one of their funerals. Guys, if you don't think driving is a big responsibility, don't get a driver's license. It's that big a responsibility. Okay? You're driving a car. A car is a deadly weapon. Make no mistake. They're big, they're heavy. Okay? You have to be responsible when you're driving it. And by responsible, I mean you're paying freaking attention when you're behind the wheel. Not doing what I see so many of you doing when I'm on parking lot supervision. You know. This. Yeah, I see a lot of you doing that. Okay? It makes me want to jump in front of your car. Okay? Yeah, to teach you a lesson. Yeah. Now, I'm going to show you something here. I'm going to use. What am I going to use this one? Oh, I did this one already? Yeah. You did really good, that's right. Yeah. Okay, we already did that. Okay. Good reaction. Right. Okay. So, just so you know, because Mr. Reel and I nearly got run over by somebody on Monday when we were in parking lot supervision. Yeah, because they were. Well, it wasn't good. They were actually good. Yeah. So anyway. Paying attention while you're driving, okay? Because this is all assuming that you react instantly, okay? And you stop right away. But okay, oftentimes people are not paying attention, and that can make a big difference. All right. So kinetic energy is energy due to motion. Okay? Anything that's moving has kinetic energy. Okay? If we're looking at like a roller coaster as an example, right? When you're at the highest point on the roller coaster, that's where you have the least amount of kinetic energy, but the most potential. And then as you go down the hill, okay, that potential gets turned into kinetic. When you're at the lowest point on the ride, that's where you'll have the most kinetic energy. Where are you going the fastest? Right at the bottom, where you have the most kinetic energy. It's not a coincidence. Okay? You're going to have the most kinetic energy where you're going the fastest. All right. Now, we talked about thermal energy. Okay, thermal energy has both kinetic and potential components to it. Okay, kinetic thermal energy is the energy possessed by the moving particles in a substance because of its temperature. Okay, so as they're moving around, temperature increases. Okay. Now, remember, this is our formula. We talked about it already. Okay, so kinetic energy is in joules. The mass is in kilograms. V is the speed of the object. Actually, not velocity, but speed because it's scalar. Okay, of the object in meters per second. Okay, it has to be in meters per second. Otherwise, you don't get joules. Okay, remember, a joule is a kilogram meter per second squared. Right, so if we're looking at this formula here, I'm multiplying kilograms by speed squared. Well, speed is meters per second. Speed squared is, which is still joules, right? Kilogram meters squared per second squared. All right. Oh, look. From the last time. Same demo. Okay. I want you to write this example down. We'll walk through it together here in a minute, but I want you to write it down. All right, so what we have here is a very typical work energy theorem problem. Okay, so it's a word problem, but it's a work energy theorem word problem. First thing I want to do is write down all the things I'm given. Okay, so first off it says a rubber band is stretched 0.85 meters. What does meters measure? Distance. Okay, so they gave me a distance there. 0.85 meters. All right, by a force of 60 newtons. So they just gave me, not energy, force. Okay, they gave me force. It says a force of 60 newtons. Newtons are the units for force. Okay. All right. At what speed would it propel a 0.125 kilogram ball? So they just gave me a mass. Okay, and they're looking for a speed, okay, that it would propel it at if it was released. Okay. So if I pull back on a rubber band, what am I doing? Besides pulling back on a rubber band. Stretching it, thinking of a four-letter word, starts with W. Keep your mind spinning. Work, yeah. Okay? I'm doing work. I'm exerting a force over a distance. Okay. If I put a ball in that rubber band and stretch the rubber band back, now I've done work. So there's now potential energy in the rubber band. If I let it go, what's the rubber band going to do? It's going to snap back to its original shape. While it's doing that, will it exert a force on the ball over a distance? So it'll do work on the ball. What will change about the ball? And if its speed changes, what kind of energy about the ball is changing? It's kinetic energy. All right. So work energy theorem problems involve you having to walk kind of through that process in your mind, real visualization, okay, of kind of what's happening. But in the end, what we have is work changing the kinetic energy of an object. Okay, that little triangle is delta, and it's changed. Okay, so expanding this out, what we're saying is work equals the final kinetic energy minus the initial kinetic energy. Now, the initial kinetic energy would be the energy the ball has when I'm holding it in the stretched rubber band. How much kinetic energy does the ball have at that point? None. It isn't moving yet. All the energy is potential, and it's all in the rubber band. Okay, none of it is in the ball yet. So EK initial then is 0. So I'm just going to get rid of it. All right. Do I have a formula to calculate work? What is it? Force times distance. Do I have a formula that calculates kinetic energy? This one. Okay, the one we just used a minute ago. Okay, 1/2 mv squared. Now I put the F there because that's the final speed of the ball. All right. I have D, I have F, I have M. Can I solve for V? Is that what they want me to find? Yeah. Okay, so how do I get VF by itself? Okay, divide by 1/2 of M. Do that to both sides. All right, that solves for V squared. I just want V, so what do I have to do? Square root. All right, so VF is going to equal the square root of 60 newtons times 0.85 meters, so force times distance, divided by 1/2 times the mass, which was 0.125. All right, now you do have to outsmart your calculator again. Okay, make sure it does it like this. Now, I would suggest not trying to do this all in one step. Okay, because inevitably you're going to screw something up in the data entry part of this. Okay, so what I usually do is I go like 60 times 0.85, I get my answer. Okay, and then I divide that by 0.5 times 0.125. And then I square root that. Okay, so the ball is going to leave the rubber band at a speed of 29 meters per second. I think we only have two significant figures there, do we? Yeah. Okay, so shouldn't be 28.6, should be 29 meters per second. Everybody follow me there? Okay, so work energy theorem problems always work this way. Okay, we look at the situation, write down what we have. Okay, we're going to have force, we're going to have distance, we're going to have mass. Okay, or we're going to have velocity and not have force. We're going to be solving for one of those things. Okay, and then we have to figure out, okay, work's being done, it's changing the energy, and set it equal to each other. Set force times distance equal to the change in energy, and solve for whatever it is you need. Right, they all basically set up the same way. One of the trickiest parts is actually identifying what type of energy is being changed, potential or kinetic. All right, I want you guys to try this one. So the tractor pushes a rock. Okay, the rock has a mass of 550 kilograms from rest to a speed of 4 meters per second over a distance of 25 meters. What force was exerted by the tractor? Okay, so first step, what kind of energy is being changed for the rock? Kinetic or potential? It's kinetic energy changing. It's accelerating from rest to 4 meters per second. Anytime our speed changes, we have a change in kinetic energy. It doesn't say anything about pushing it uphill or lifting it, so it's not changing any potential energy. Everybody kind of follow me there? Okay. So we want to start out, we want to write down our givens. So the rock has a mass of 550 kilograms. Okay, its initial speed is 0 meters per second. Its final speed is 4 meters per second. And the distance over which it is pushed is 25 meters. Right? We are looking for the force being used. So we've already established that the work being done by the tractor is going to change the kinetic energy of the rock. It's going to speed up from 0 to 4 meters per second. So that's going to mean force times distance equals 1/2 mvf squared minus 1/2 mvi squared, because change means final minus initial. Initially, the rock was moving at, all right, did it have any kinetic energy? All right, so then I don't need to worry about subtracting 0. I'm just going to get rid of it and simplify my life. Okay? I want to solve for force. How do I get force by itself? So divide both sides by d. Okay, so force is going to equal 1/2 times 550 times 4 squared divided by 25. 0.5 times 550 times 16 divided by 25. All right, so we're looking at 176 newtons, which is a really wimpy tractor. Like, really, really wimpy. Okay, everybody follow what we did there? No? Okay, where did I lose Brad? Just everywhere? Okay. So, first thing I did is when I read the question, I tried to figure out, am I changing the height the object is at or the speed the object is moving? Because that tells me whether I need to set work equal to kinetic energy or potential. So anytime there's a change in speed, I'm changing the kinetic energy. Right? So that was my first step. Then I wrote down what I had, okay, and established that I had everything except for force. Then I expanded out this formula. I said, okay, work is force times distance. Okay, and I said the change in kinetic energy is the final kinetic energy, 1/2 mvf squared, minus the initial, 1/2 mvi. Since it wasn't moving at the beginning, it didn't have any kinetic energy at the beginning, so I took that off. Okay, then I just manipulated for the thing I didn't have. Okay, so the work being done was what was causing the rock to go faster. And so I solved for how much force was needed to make the rock go faster. Okay?
When you go into a square root, like let's take the square root.
Oh, the only time you would have to do a square root is if you were solving for something that was squared. So you're solving for p.
What was the equation that you had at the top of that question?
It was the same one that I started with here. So the change in energy is final minus initial. Right? So I had that here when I had minus 1/2 mvi. I had that there, but vi was 0, so I took it off. Okay, so mathematically, are we doing anything crazy? No, like the algebra here is not the difficult part. The difficult part is seeing the physics, okay? Being able to visualize what's going on, identify what type of energy is changing, and go from there. Okay, so try this one. We have a mail carrier that picks up a 10-kilogram package on the 3rd floor of a building where they are 30 meters above the ground. They deliver it to the 10th floor that's 100 meters above the ground. How much work is done? This actually has less steps than the last one. We always do. Okay. So, if I'm taking something from one height to another height, what type of energy am I changing? Potential. It doesn't mention anything in here about any changes in speed. Right? So there's no change in kinetic energy. The box is being lifted from one floor to the next. Okay? And that's all. So that's my first step, is identifying that the work in this question is changing the potential energy of the object. Right? Now I'll write down the givens. Right, so we got a mass of 10 kilograms. Okay, we have an initial height of 30 meters. We have a final height of 100 meters. Okay, and we also know that gravity is 9.81 meters per second squared. All right, we're looking for how much work is being done. All right, so work is equal to the change in potential energy. Do I have a formula that calculates potential energy? Yeah, what is it? M times G times H. All right, so the work is going to equal my final potential minus my initial potential. Everybody okay with that? Okay, so that's going to mean then that work will equal M times G times the final height minus M times G times the initial height, the change in energy. All right, this will calculate the energy I have on the 10th floor. This will calculate the energy I have on the 3rd floor. The difference between them is how much work I do. Okay, don't have to solve for a force here. It just asks for how much work I would be doing in moving the box from one floor to the next.
Could you just take the height of the first one?
Yeah, you could. You can do that with potential. The reason I don't always show that is because people think it applies when they're doing kinetic, and it doesn't because it's exponential. It's different. Okay, but yes, you're right. You could just go M times G times, and you get the same answer. Yes. Okay. I'm not going to do it that way just for simplicity here. Okay. All right. So when we plug in our numbers, we're going to have 10 times 9.81 times 100 minus 10 times 9.81 times 30. And times 9.81 times 100, okay, plus, sorry, minus. Okay, I also could have gone 10 times 9.81 times 70. I would have got the same answer. Okay, so 6,867, but I only have how many significant figures? 2. So this is going to be 6.9 times 10 to the 3. 10 to the 3 what? Joules. Okay? So again, first step, identify what type of energy the work is changing. Write down your givens, and then establish your equation. Work will equal the change in whatever energy. Okay, start putting in your numbers and solving. Right? They all work the same way. Okay, so try this one. Bulldozer does 7,500 joules of work. So they're giving me the work in this one. Okay, in pushing a truck from a speed of 2 meters per second to an unknown speed. If the truck has a mass of 2,500 kilograms, what is its final speed? Okay. The answer is 3.16 meters per second. So if you get to that point and you get that number, get it right. All right. So in this question, what kind of energy is being changed? The kinetic energy of the truck is being changed. All right. So work is going to equal our change in kinetic energy. Right? So that's going to mean work equals the final kinetic energy minus the initial kinetic energy. Right? And that's going to equal 1/2 mvf squared minus 1/2 mvi squared. Okay? Now, the things given to me in this question are, first off, the work. 7,500 joules. Okay? We know the initial speed, 2 meters per second. We're looking for the final speed. And we know the mass of the truck is 2,500 kilograms. Okay. So, I know this number. I know what W is. And I have enough information to calculate what EK final is. Right? So, what I'm looking for is VI. It's part of this. How do I get this by itself? Can I move this over to the other side? Okay. Or can I just switch these two things and say that if I take my final kinetic energy and subtract the work, that would leave me with my initial? Sorry, I'm not looking for VI. Sorry, I'm looking for VF. Sorry. I'm looking for this. All right. So if I want to get VF, it's part of this. So what do I do with this? I move it over to the other side. I add it because the initial kinetic plus the work will give me the final. Right? So work plus 1/2 mvi squared equals 1/2 mvf squared. How do I get VF by itself? Divide by half of m. And then, okay, always the same steps. I identified what type of energy was changing. I put in what I knew. I manipulated to find what I was looking for. Right? Always the same set of steps. So when I do that, okay, numbers plugged in, it's going to be 7,500 minus 1/2 times 2,500 times 2 squared divided by 1/2 times 2,500. So 7,500 minus 0.5 times 2,500 times 4, okay, divided by 1250, that's half of 2,500. Okay, and then
Oh, yes, you have an extra.
I have an extra. Where do I have an extra something?
No. You have an extra 0.
An extra 0. Do I have a number wrong in here?
No? I got it.
I must have. Try it again. 5 times 2,500. That is 5,000. I must have put something wrong here. I'm entering something wrong somewhere. Hey, sorry guys, valves are not working, so you gotta take off. We'll look it out tomorrow.